Hello everyone. In this video we will talk about the last of the derivative rules to be seen this semester. This is called the chain rule. By now we've covered derivatives for most functions as well as their combinations. So we've covered sums, constant multiples of functions, differences, products, quotients, but we never talked about their compositions, that is, derivatives that involve a function acting on another, of the kind f of g of x. Here is what the chain rule states. If g is a function that is differentiable at x, and if f is a function that is differentiable at g of x, then the composition of the two, f of g of x, has a derivative whose result is f prime at g of x times g prime at x. What you should denote here is that because we have layers of functions, g of x followed by f acting on the result, we have to work by layers, and we work our way outside in. So the derivative of f is performed first, calculated at g of x, and then we look at the inner function g of x, perform its own derivative, g prime, whose result is multiplied with the first derivative, f prime of g of x. Here's the proof of the chain rule, which is for your information only. So let's define c of x, so the composition function, as being f of g of x. Alright, so here is what the definition would say. C prime at x, so the derivative of function c of x, is the limit as b approaches x, c of b minus c of x over b minus x. This is the typical delta y over delta x form that will generate the tangent line as the average rate of change is slowly turned into the slope of a tangent line through the limit process. C at b and c at x can be replaced by how the function was defined, so f of g at b minus f of g at x. The problem at this stage is that although the quotient seems familiar, it doesn't actually respect the limit definition that we know for derivatives, because the argument within the f is not acting at the denominator. So we're going to cheat a little bit, and we're going to divide by g of b minus g of x, so that now the content of function f at the numerator is replicated at the bottom, and of course to compensate we also have to multiply by g of b minus g of x. This is a product of two functions, and a limit acting on this product of two functions can then be distributed into two different limits. So as b goes towards x, we now have two limits acting on different ratios, on different rates of change or average rates of change. The second limit is probably the easier of the two to recognize. That would be g prime at x. The form satisfies perfectly the derivative definition, or the limit definition of the derivative. b is approaching x. As it does so, g of b minus g of x creates a point where the secant line will become tangent. The first limit is not as easy to see, but as b approaches x, g of b has no choice but to approach g of x. Since g is differentiable, it's also continuous. So the first limit can actually be replaced by g of b heading towards g of x. And although the letters and the labeling is a little bit more complicated, now the first limit is that of a derivative. It's the derivative of function x, but calculated at g of x. And here we have our chain rule. So we've just differentiated f of g of x and shown that the outcome will be the derivative of the outer function with g of x as its argument, followed by the derivative of g calculated at x. I will very seldom use this notation. Actually, most of the times I'll be saying that the inner function can be thought of as some expression u. It's a function of x, but I'll be naming it or stating it as u, the inner function. And rather than saying f prime at g of x, we'll just say f prime at u times u prime, which is the effect of the chain rule. So here are all the rules that you've learned for the basic functions, and some of these are extensions of others. For example, tan, cotan, secant, cosecant are compositions, they're quotients of sines and cosines, and the quotient rule has allowed us to demonstrate those for additional functions. Whenever a composition of functions is involved with these functions, then rather than thinking of x, we will think of u as being the content of them. And notice how the formulas themselves stay exactly the same, except for the incorporation of the u prime term. So the chain rule aspect that is applied to a composition of functions. Here's how we actually put this into practice. As a first example, let's examine how we would differentiate sine of x cubed. Sine of x is a basic rule whose derivative would be cos of x. However, this time we have a function contained inside the sine function, which is the x cubed term. This is what I'll refer to as being u. It is the inner function that the sine function contains. So to simplify our visualization here, let's think of differentiating sine of function u, sine of u. If the derivative of sine of x is cos of x, then the derivative of sine of u will be cos of u. However, because u is a function of x itself, we must think of applying the chain rule, which is the u prime term. So sine of x differentiated is cos of x, sine of u differentiated is cos of u times u prime. As for the u prime, that's a basic product rule. So observe how cosine, we're not doing cosine of 3x squared. So the derivative of the inner function occurs at a second step. Let's differentiate the root of x squared tan of x plus 1. So can you figure out who the inner function is in this example? This is definitely not a basic rule. We know how to differentiate root of x, but this is root of something much more elaborate than just root of x. So to start off with, let's think of the root as being a power. X squared tan of x plus 1 happens to be the function contained inside the power. So we can think of this as u. Again, to simplify our visualization, I'll try not to think of blah 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 to the half, but rather u to the half. The derivative of x to the half is 1/2 x to the minus half. So why wouldn't the rule be the same if we have u instead? 1/2 u to the minus 1/2 is the exact same basic power rule we would have used in the past. Except this time, since u is a function of x of its own, its derivative must follow. So times u prime. 1/2 u to the minus half times u prime. When it comes time to differentiating function u, then other basic rules may fall into place. For example, in this case we have a product rule of x squared times tan of x, and the derivative of 1 is 0. Here's one last example that will involve the use of the chain rule. So here we have 2 to the power x cubed plus x cubed times secant of 4x. Keep in mind that we have actually an addition here. It's an addition of two separate functions, 2 to the x cubed on the one hand, and x cubed secant 4x on the other. So the first rule that would be prescribed here would be the sum rule, which splits up the two functions into two individual derivatives. I've highlighted in red the x cubed in the first expression because 2 to the power x would have been a basic rule. That would have been 2 to the power x ln of 2 when differentiated. Unfortunately, we have to think of x cubed as being an inner function called u. Therefore, 2 to the power u its derivative will be 2 to the u ln of 2 times u prime. 2 to the power x, the derivative of 2 to the power x would have been 2 to the power x ln of 2. When u is involved, the form is maintained, so 2 to the u ln of 2, but with the addition of a u prime expression. As for x squared times secant of 4x, that's a product. And as a result, I've applied the product rule to the product of x squared with secant 4x to split it up into two separate derivatives. One derivative on x squared leaving secant untouched, one derivative on secant 4x leaving x squared untouched. Once more, I've highlighted the argument inside the secant, the 4x, because that's not a basic function. Secant x would be a basic function. Secant 4x is actually a composition. All right, the first terms, all that was left was for us to differentiate x cubed, which has become 3x squared. The derivative of x squared is 2x in the second term. That was straightforward enough. In the last term, secant of 4x, we have to think of differentiating it as secant u. The derivative of secant x would have been secant x tan x. The derivative of secant u is secant u tan u times u prime, which explains how the last term of this third expression is obtained. And following through with the last derivative acting on 4x, we would have an extra 4.